Today I'm going to present another sampling-based path planning algorithm, which is called the bidirectional RRT. This one is a variant of the RRT algorithm discussed in an earlier video. This is presented by me, Ashraf Faraj, on January 20, 2024. So as usual, the problem setting is we're trying to find a collision-free path from the start to the goal, avoiding the red obstacles. Now this figure right here shows an example of a path generated by a bidirectional RRT algorithm. Now the idea in this case that we have two trees, one we call a forward tree right here with the black edges with a root at the start node, and another tree, the backward tree, here having blue edges, which starts at the goal node. The idea is that both trees will try to expand until they both meet at some point. And once they meet, we can traverse a path from the start node to the meeting point, and then from the meeting point to the goal node. Now we're going to discuss the bi-RRT algorithm in detail. So first of all, we're going to initialize the forward nodes as start and the forward edges as an empty list. Then we're going to initialize the backward nodes as goal and the backward edges as an empty list. Then we're going to initialize the forward and backward tree using the nodes and edges that we just defined. Next, we're going to repeat the following steps for a maximum number of iterations n max. The first step is to sample from the free configuration space with a little bit of adjustment. So in this case, we're going to, most of the time, sample randomly from the free configuration space, and with a low probability, sample from the opposing tree. So if, for example, we're trying to grow the forward tree, we're going to sample from the free configuration space with a probability of 0.9, or we're going to sample from the backward tree with a probability of 0.1. This is to try to connect both the forward and backward tree and hence find a viable path. In this case, our sampling function returns a random point and a boolean that indicates whether this random point is actually from the opposing tree or just a random point from the configuration space. Next, as in the normal RRT, we're going to find the nearest node from the forward tree to this newly generated random point. We're going to call it xparent. Then, as usual, we're going to attempt an extension to this newly generated point, which is going to return the planned point and a boolean possible indicating whether there was a success in this planning or not. We must note here that in case we are actually choosing a point from the other tree, the opposing tree, then we're going to try to extend directly to that node and not in between. So in this case, we're going to try to find exactly a path between xparent and xrand. Now, if this attempt of extension was possible, we're going to update our tree and we're going to check whether this random point that we just extended to was actually from the opposing tree. If it is, then we've actually found the goal, because now we can connect the forward and backward tree and just traverse the path from the goal, from the start to the goal. Now that's actually step 4. Now we repeat those steps from 1 to 4 for the backward tree. Finally, we just concatenate both trees while reversing the node order in the backward tree and perform an A search to plan the shortest path in the resulting graph. Now for the results, the figure on the right shows the path generated by this bidirectional RRT algorithm on our example. As we can see, we have the black edges here indicate the forward tree, which was grown starting from the start node, and the green edges here show the backward tree, which was actually extended from the goal node. The blue path shows the path that was found by using an air search on the concatenated graph. We can see here that both trees were able to join at this edge right here when they attempted to connect to each other. Now to the conclusion, in this project we presented the bi-RRT algorithm and we discussed its implementation in detail. We also tested it on a kilobot path planning problem with circular obstacles. And that's it. Thank you for listening.